Hi to everyone and warm greetings to all. Today I'm going to talk on the topic hybridization. Hybridization is one of the interesting topic that one will come across learning of chemistry, and generally this hybridization is the concept that has been used both in organic chemistry and inorganic chemistry. And hybridization will tell us about the concept in which the transfer of electrons will take place from one orbital to another orbital within the shell of an atom. Topic outline. Under this topic, hybridization, first of all, we look at the introduction part. Under the introduction, we will try to discuss some of the back philosophical foundation in which these topics were actually introduced. And we'll also look at some of the brief scope or the importance of this particular topic, and then we'll define what is meant by hybridization. We'll look at the definition. We will also discuss hybridization and how this hybridization are actually determined by steric number. We will try to discuss hybridization in some of the molecules, especially organic compounds. Then we'll try to solve some practice questions, and finally we'll look at the lesson summary, or simply we call as conclusion. Okay, now let us look at the introduction. In one of the class, if you remember, we were discussing about this valence bond theory. Valence bond theory is one of the important topics that has contributed tremendous in understanding the nature of chemical bonding. It generally explains us about how these reactions are actually taking part in terms of the orbitals, and it also explains us about how these orbitals actually mix together to undergo the chemical reactions, or simply we call as how these chemical bonds are formed. But having said that, valence bond theory actually has some of the drawbacks, limitations, and one of them is it failed to explain the theta valency exhibited by carbon atom, and this was one of the limitations of valence bond theory. So a guy known as Linus Pauling, he is an American chemist, and he's one of the significant figure in chemistry field. He was awarded Nobel Prize for two times, one in 1954 and one in 1962, for the enormous contribution that he had made to the chemistry field. And this guy, he just expanded this valence bond theory by introducing a term known as hybridization. Hybridization. Now you must be wondering now, what is this hybridization? Now, to get more picture, to get more idea about what is this hybridization, we look at the background study, or simply we can say that the philosophical foundation in which this hybridization was actually introduced. Okay, this is the background, or simply we can say as the background or the study background behind the introduction of hybridization. So it is mentioned here, the electronic configuration of carbon is 1s squared, 2s squared, 2px1, 2py1, 2pz0, as its atomic number is 6. We know that as the bonds are formed by unpaired electrons, carbon should show a valency of 2. Because if you look at the electronic configuration, we have two unpaired electrons. The expected valency is 2. But we observe that carbon shows theta valency in its compounds like methane and carbon dioxide. This was explained by saying that the above mentioned configuration is the configuration in ground state. So here comes the term known as ground state, and we'll come to know another term which is known as excited state. So during the formation of bonds with other atoms, some of the electrons in lower energy levels are excited to higher levels. Thus, in case of carbon, one electron from 2s level is excited to empty 2z orbital. So which means from 2s it's given to 2pz, which was initially it was empty. Now there are 4 electrons which are unpaired. These 4 electrons will form 4 bonds by overlapping with the orbitals of other atoms. For example, they combine with 4 hydrogen atoms to form methane. However, there is one thing which is surprising. We know that the tetravalency was solved, but the problem is here again. One thing they have found out is we find that in methane all the CH bonds have the same bond energy and all the angles CH are same. The angle between the CH were actually found to be same, that is 109 degree and 228 inches. Looking back at the orbitals which participate in bonding, that is one s orbital and 3p orbitals which have different shapes and energy, we expect one of the bonds formed by the s orbital to be different from the 3 bonds formed by p orbitals. Moreover, as the p orbitals are inclined at an angle of 90 degrees to each other, we expect the bond angles of 90 degrees in methane also. But this actually is not happened. This was not observed. Thus, to explain this anomaly, the concept of hybridization was actually introduced. After the introduction of hybridization, this phenomenon explains satisfactorily why the bond energies and bond angles are equal in case of methane and many other molecules. So this hybridization has contributed in solving especially the bond energies and the bond angles found in the compounds, be it organic compounds or the inorganic compounds. Okay, now we have understood what is meant by hybridization, that why this hybridization was actually introduced by Linus Pauling. We have looked at the study, the background study of why this concept was actually introduced. Now next, what is hybridization? What is hybridization? If you look at the definition here. The concept of intermixing of two or more atomic orbitals of an atom with almost same energy to give same number of identical and degenerate new type of orbitals. So here what I remember is, in this case, just remember here the intermixing of two or more orbitals will take place within the atoms. And in the process, what they will do is they will try to form same number of identical and degenerate new type of orbitals. So which means that the number is going to be same, and only thing is it will be degenerated, which means it is going to be new. If you look at this sentence, it's mentioned that hybrid orbitals have different energies, shapes, etc. than the component atomic orbitals, which means this particular orbitals, which is formed because of the intermixing of orbitals, they are going to have different energies as well as shape. Okay, now to get some basic idea before we go to the depth of this particular topic, let us look at, we have understood definition, we have look at the definition. So to get more idea, we look at this video, we try to analyze this video and then find out more features of this hybridization.
Hybrid orbitals are formed by a mixing of the hydrogen-like s, p, and d orbitals that characterize a free atom. The three p orbitals are directed along the x, y, and z axes. When we mix an s and a px orbital, we produce two hybrid orbitals called sp pointed in opposite directions along the x-axis. Mixing of an s with the px and py orbitals produces three equivalent hybrid orbitals in the xy plane. We call these sp2 hybrid orbitals. Notice that the hybrid orbitals have major lobes, which contain most of the electron density in the orbital. These are used in bonding to other atoms. Mixing of the s with all three p orbitals results in formation of four equivalent sp3 hybrid orbitals, directed toward the apices of a tetrahedron.
Now we look at the conditions required for the hybridization. So the first condition that is required by the atoms to undergo hybridization is the orbitals taking part in hybridization must possess almost similar energy. So which means this particular hybridization will only take place in the orbitals which has almost similar energy. For instance, the 1s and 2p, if you look at this diagram, 1s is way down and 2p is way above. In between we have 2s here. So the energy level between 1s and 2p is much more different. That's why the hybridization is not going to take place. Instead, since 2s and 2p energy level is almost similar, almost same, the hybridization is going to likely take place between 2s and 2p. This is the first condition. Second condition, it can take place between completely filled, half filled, or empty orbitals. So hybridization can take place in all the three cases, be it completely filled, be it half filled, or empty filled. I mean, so empty orbitals. Third condition is whereas the pair electrons do not take part in bonding, they can take part in hybridization. This happens in the case of ammonia and water. So this what this third point is going to tell, it's telling here is in case of ammonia, like ammonia and water, in that case they still have lone pair which do not take part in the chemical reactions. It stays, it remains as a lone pair, but they also participate to undergo the hybridization. So this happens especially like in some of the compounds like water and ammonia. Okay, now we look at types of hybridization. We have sp hybridization, we have sp2 hybridization, sp3 hybridization, sp3d hybridization, and we have sp3d2 hybridization. So these are the 5 types of hybridization I'm going to discuss. And out of this many, sp, sp2, sp3 are the most discussed topics or the types of hybridization you will see across many of the literature. But having said that, I'm going to touch upon all these 5 types of hybridization. First type is we have sp hybridization. So in sp hybridization, remember that we've already understood what is meant by hybridization. So here in this case, the title said is sp. So in this case of hybridization, 1s and 1p orbitals of almost equal energy will try to react together, not react, they will try to mix together, and then they generate identical number of hybrid orbitals. So which means this 1s and 1p will combine together and then they form two sp hybrid orbitals, and their shapes are linearly arranged. If you look at this blue diagram there, you'll see that the shapes are linearly arranged, and the angle between these hybrid orbitals are 180 degree. And they possess 50% of S character and 50% of P character, because here we have one S and one P equal, so which means it's going to have 50%, 50% of each of these orbitals. Second type, we have sp2 hybridization. If you have understood the first type of hybridization, here just remember now, it's just the difference between among this many hybridization is you just see the number here, different in number. In this case, we have sp2. So sp2 here means 1s and 2p. So this 1s and 2p orbital and intermix together, and they are going to form hybrid orbitals. Hybrid orbitals. And if you look at this blue diagram, we have 1s there, we have 2p, they're trying to mix together, and then they form 3 sp2 hybrid orbitals. And the shape is going to be trigonal planar symmetry, and the angles between or among between the two hybridized orbital is going to be 120 degree, and in this case it's going to be 33.3% of S character and 66.6% of P character. The third type of hybridization we have here is sp3 hybridization. So in this case, the intermixing is taken place among the 1s and 3p orbitals, and after combination of these many orbitals, they're going to form the 4 sp3 hybridization hybrid orbitals. If you look at that diagram, blue diagram, 1s and 3p, they are combining together, and then they form this above sp3 hybrid orbitals. And the shape of this sp3 hybridized orbital is going to be tetrahedral symmetry, and the angle between each of these orbitals is going to be 109 degree and 228 inches. The sp3 hybridized orbitals have 25% S character and 75% P character. Okay, next we have here is sp3d hybridization. Now, if you have understood the trends, how these hybridizations are formed, this is very simple. Just on top of sp3, we're going to add one more d orbital. So this type of hybridization is actually termed as sp3d hybridization. An example they have given here, this is more important. Please remember this, it's very important when we discuss about the compound. Where we will discuss about this singlet and singlet linkage and all later on. So this will definitely help you in building some basic foundation to understand that concept. So the example taken here is phosphorus pentachloride, and this phosphorus act as a central atom here. And if you look at the electronic configuration, especially for the valence shell, we have 3s square and 3p3. In case of ground state, in excited state, now the valence shell, if you look at the valence shell now, so from 3s, one of the electron is now given to, or is shared to 3d, excited to 3d. So which means we have how many electrons are there now? We have 5 ampere electrons. So these 5 ampere electrons will now try to intermix together. They will try to mix together, hybridize together, and in the process they undergo sp3d hybridize. In continuation to sp3d hybridization, here we have some more examples that will get more idea. So in this type of orbitals, what happened is the mixing of sp and d orbitals form trigonal bipyramidal symmetry. So this is going to be, the shape is going to be trigonal bipyramidal. Three hybrid orbitals lie in the horizontal plane, inclined at an angle of 120 degrees. So if you look at this diagram, blue diagram, look at this blue diagram, you see that three of these orbitals are arranged horizontally in the plane, and the angle between this, among these three, between the two hybridized orbital is going to be 120 degree. And the remaining two orbitals are present above and below the trigonal plane at right angles. So that is going to be right angles, and they're just below and above the this line of the horizontal plane. And in this case, the orbitals have 20% of S character, 60% of P, and 20% of D characters. And yes, this is the fifth type of hybridization, which is called as sp3d2 hybridization. So in this case, the intermixing of orbitals is among the 1s, 3p, and 2d. So they are going to intermix together, and then they form, yes, hybrid orbitals. The example they have given here is taken for sulfur hexafluoride. Sulfur hexafluoride. If you look at the electronic configuration at ground state, you'll see that it's going to have 3s squared, 3p4, and 3d0. But if you look at the excited state, you'll see that there is 1s squared, there's 3s1, then we have 3p3, then we have 3d2. So which means 1 from the 3s is excited to 3d, and similarly 1 from the 3p is excited to 3d. Now we have how many unpaired electrons? We have in total 5 unpaired electrons. So this 5 unpaired electrons is going to hybridize. Orbitals is going to hybridize. These orbitals, unpaired orbitals, is going to mix together, and then they're going to form sp3d2 hybridization. In continuation to sp3d2 hybridization, here are some more points. These 6 sp3d2 orbitals are directed towards the corner of a octahedron. Please remember their shape is going to be octahedron in shape. As you'll see the diagram there, the three-dimensional diagram with the green and yellow color. So that is the octahedral arrangement of the hybridized orbital. They are inclined at an angle of 90 degrees to each to one another. So which means these hybridized orbitals, 6 hybridized orbitals will be arranged in such a way that the angle between two hybridized orbitals is going to be 90 degrees. Okay, so that's all about the types of hybridization that I have to explain, and to get more idea, to get more concept, to just check whether we have really understood, whether the transfer of learning has taken place. Just look at this, watch at this video, and then try to analyze further. Here's the video that I have downloaded from one of the YouTube channel, so you can go through this. 5 types of hybridization. I've already explained SP hybridization. So this is the SP hybridization. In case of SP hybridization, we have already learned that 1s and 1p will intermix. Let us see this diagram demonstration, three-dimensional demonstration. So as you will see there, 1s is above the right hand corner and 1p below the left hand corner. So these two will mix together, So in this case, these two is mixing together, and then they're going to form two sp hybridized orbital, as you will see in that diagram there. This is how sp hybridization is taking place within the atoms. This is the structure of actually this particular one of the atoms that they're given. And second type of hybridization we have here is sp2 hybridization. If you remember, we have discussed that in case of this type of hybridization, they're going to have 1s and 2p. So let us see. So here we have 1s and 2p. So this 1s and 2p, they're going to intermix together, and then they're going to form 3 sp2 hybridize. And this is how the arrangement of orbitals are found. Hybridized orbital, and the other two are actually unhybridized p orbitals that we will discuss later on when you try to solve some questions. sp3 hybridization. So in this case, the hybridization is going to be formed, or it's going to be taking place among 1s and 3p. So it is, as you see here, we have 3p and 1s. So they will intermix together, and the possible hybridized orbital is 4sp hybridized. We've also discussed shape. What type of shape is this? So this is how these orbitals are actually arranged. sp3 dehybridization. So let us look at how this sp3 dehybridization actually formed. In this case, they're going to the hybridization is going to form by 1s, 3p orbitals, and 1d orbital. This is going to show the orbital. sp3 dehybridized orbital. Okay, you must be wondering now the diagram is coming to be very different here. So this, the right hand side, it represents sp3 sp3 hybridized, which we have already discussed, and the left hand side is it represents one of the d orbitals. On the d orbitals we have discussed, there are 5 sub orbitals that we'll discuss later on if the time permits. But here what you have to remember is, in this case, the right hand side is representing the sp3 and the left hand side is representing the d orbital. So these orbitals are going to intermix together within the shell of an atom, and this is how these structures are actually arranged. And the expected hybridized orbitals are 5. Right? We have 1s, 3p, and 1d. So in total we have 5 sp3 d hybridized orbital. And this is how these orbitals are actually arranged. And the last one is sp3 d2 hybridization. This is how the sp3 d2 hybridization models looks like. And here just remember that the hybridized orbital, or the hybridization is taken place among 1s orbital, 3p orbital, and 2d orbitals. Okay, so as I've already discussed, the left hand side represent sp3 hybridized, and the right hand side represent g2 orbitals. So these two will intermix together, and the expected hybridization is going to be 6 hybridized, right? Because we have 1s, 3p, 2d. When we combine this, we get 6 hybridized orbitals. This is how the hybridizations actually can be explained with the three-dimensional diagram. I hope this makes some sense to you. Okay, now we have discussed about the types of hybridization, and we have also watched a short video which explain this concept in terms of three-dimensional diagram. Now, yes, the next topic we have here is a very interesting topic. Hybridization determined by string number. Hybridization is also determined by, beside the 5 types of hybridization here, the hybridization can be also determined by string number. Now, what is string number actually? So the string number is nothing but it is the number of sigma bonds surrounding the atom plus number of lone pair of the atoms. So for the particular atoms, this particular atom is going to have bonds, especially sigma bond. If you remember, we have 2 types of bonds we have discussed. One is pi and one is sigma. Here we are discussing in terms of sigma bonds. That particular atom is going to have a sigma bond, as well as this particular atom will also have some lone pairs. So this number of lone pair and the number of sigma bond that is around that particular atom is actually termed as string number. And this string number will also determine the hybridization. Okay, the example they have taken here is carbon. Because of string number, hybridization can be found. Different type of hybridization can be found in the multiple atoms such as carbon, nitrogen, and also oxygen, and some more. But here we're going to discuss in relation to carbon. The individual carbon atom acting as a central atom can exhibit, depending upon the string number, it can exhibit different type of hybridization such as sp3, sp2, and sp. First one, how carbon exhibit sp3 hybridization. Here it's explained here. When carbon is bonded to 4 other atoms with no lone electron pairs, the hybridization is sp3, and the rearrangement. The arrangement is tetrahedral, which means we have already learned the tetracovalence, right? Tetravalence of carbon. So when this carbon 4 valency bond is formed with the other atoms, the valence bond, 4 valence bond is formed from this carbon. So this type of compound will actually exhibit sp3 hybridization. Next, carbon will also exhibit the sp2 hybridization. The condition says that a carbon atom bound to 3 atoms, 2 single bond and one double bond is sp2 hybridized and forms a flat trigonal or triangular arrangement with 120-degree angles between bonds. So here just remember, in previous case, all there is going to have one single bond around the carbon atoms, but in this case, around the carbon atom, one is going to be double bond and the other is going to be 2 single bonds, which means we have 3 atoms around this carbon atom. So this type of compound is going to exhibit sp2 hybridized. Carbon will also exhibit sp hybridization. So the third possible arrangement for carbon is sp hybridization. which occurs when carbon is bonded to two other atoms, which means here carbon is likely being bonded to only two atoms. One of the atom is bonded by double bond. I mean, both atoms can be bonded by double bond, or it can be in such a way that one of the carbon is bonded to one atom with single bond, and the other one is bonded by triple bond, which means for this particular carbon, it's going to have only two atoms bonded. So, which means this type of compound, which have carbon bonded to only two atoms, this type of compound is going to be called sp hybridization. So this, when you try to discuss, when you try to solve some questions, especially these organic compounds such as ethane, ethyne, and all that compounds, I think you'll get more idea. Okay, so to get more idea, yes, I have already mentioned that this string number, you're going to get more idea when you discuss this type of the problem questions. So here is a question that I'm going to share with you, and then we'll try to discuss together. We'll try to find out the answer together. The answers are also given here. Answer is already provided here. So in the interest of time, I will not solve this, but the answer is already given there. Maybe you can go through this question and then try to solve. And then if you do not get the answer, please feel free to ask out that to our tutor, or you can directly ask to me. Okay, so this is the practice problem. So questions, there are 5 questions, and this practice problem is trying to discuss in terms of ethene. And here we have to remember, in this case, it's going to be the hybridization is going to discuss is going to be discussed in relation to the strict number. You can also try this question. Okay, second question is it says that explain the 5 basic shapes of hybridization. We have discussed 5 types of hybridization, and if you remember, we have discussed 5 types of hybridization, such as SP, SP2, SP3, SP3D, and SP3D2. So what are the shapes, basic shapes they are going to? The answer already given there. Maybe you can stop this slide for some time and then pause this video for some time and then look at the answer yourself. In the interest of time, I'll not explain this because we have already discussed in detail in my earlier explanation. Okay, so with this, now we'll look at the lesson summary or the conclusion of this particular topic, hybridization. The first conclusion, the key message, the point that this hybridization is trying to tell us is atomic orbitals with equal energy undergo hybridizations. Please remember the first very important point is hybridization is only possible between the atomic orbitals which have equal or similar energies. Second, hybridization theory is an integral part of organic chemistry. It explains bonding in organic compounds. Not only in organic compounds, it can be also used in inorganic compounds to especially look at their structure, especially the types of bonding they form. Hybridization is one of the factors which determine the shapes of molecules. So my presentation, I was discussing that some of the scope, the importance of hybridization. So because of this hybridization, we can also learn some of the shapes of molecules. We have already discussed, right, 5 types of hybridization, especially their shapes, linear, right? So this type of shapes that I had all the shapes we have discussed. Hybridization actually helps in determining the shapes of molecules. And finally, the last point I have here is the amount of p character or s character, which is decided mainly by orbital hybridization, can be used to reliably predict molecular properties such as acidity or basicity. If you remember in my presentation, I was discussing about the S character, how much S character, how much P characters for each of this hybridization. If you remember for S, I told you SP is going to be 50% S and 50% P. So that type of compound, what type of compound is this? Is it acidic compound or basic compound? Basic compound. So this also you can find out using the hybridization concept. To get more idea, one condition that I can share you for this fourth point is it is mentioned that higher the S character, greater will be the acidic character. So which means more the S character, this particular compound, this particular substance is going to be more acidic in character. Okay, that's all about the hybridization that I had here to discuss. I'm sure because of the time constraint and because of the limited time to be presented in terms of the presentation, you may not have got all the ideas supposed to be explained. But having said that, it's always wise to please go through this reference, browse internet, type of literature, books, and then try to get more ideas. These are the references that I have used while trying to come up with this presentation. The books and the webs and the internet resources where I try to browse and then bring this into one coherent shape. Thank you so much for your time. And yes, take care and good luck in your life.